touch sensor capacitance. Touch sensor consists of two circle electrodes placed on a dielectric board, and the capacitance between these two electrodes depends on the presence of the stylus in the vicinity of the electrodes. You can consider this sensor as a kind of capacitor. And the capacitance value doesn't depend on the voltage applied. Sensor could operate on AC voltage or on the pulsed voltage, the capacitance value will be the same. So I'm going to simulate an electrostatic problem. I will apply +1 and -1 volts to the electrodes and measure the electric field energy. The capacitance could be calculated as the stored electric field, doubled value, divided by the potential difference squared. The stylus I'm going to simulate as a conducting body with the floating boundary condition. Okay, let's start QuickField now. In QuickField, I create a new problem. Sensor. Next. Problem type is electrostatics. Length units are millimeters. Every simulated device is a three-dimensional object, but sensor features a rotational symmetry, so the model class would be axisymmetric. Finish. The problem is created, and here is the geometry model editor window. In axisymmetric problems, the axis of rotation is a horizontal one, and I should create only the upper half of the cross-section in the model. First, I will insert a rectangle with the dimensions 1 by 15 millimeters, and the insert point will be here. Insert. Close, zoom to fit. This is the cross-section of the printed circuit board. Next, I will insert another rectangle with a dimension 0.035 by 3 millimeters. Insert point will be here. Insert. This is the cross-section of the transmitting conductor, and that would be the cross-section of the receiving conductor. Okay. And I will add another rectangle that will represent a stylus, 50 by 5 millimeters, and position 3 millimeters to the right. Insert. Close. Next, I'm going to add some lines, so I switch to insert mode, zoom to fit, zoom out, and draw the line on the axis of the rotation. Here, and draw another arc here. This would be the A block. Let's zoom in, and here I will draw the stylus tip. Okay. Now the geometry model is ready, and I should assign labels to distinguish one geometric object from another. Switch to Select Objects mode. Click the object to select. This is air. This is dielectric. Inside conductors, there is no electric field, so there is no need to assign label to the conductor's body. Instead, I should assign label to the conductor's faces. So I will select with the rubber band. This way I have selected a body, a block, edges, the boundary, and vertices. And for the edges, for the boundary, I assign label. This is the transmitting conductor, TX. This is the receiving conductor, RX, receiving conductor boundary. And this is the stylus. Zoom to fit. Not for block, but for boundary. Stylus. And I will assign label to the external boundary. External. Okay. Now let's provide physical properties for these labels. Double-click the label name in the tree. The dielectric permittivity of the air is 1. The dielectric permittivity of the dielectric is 4.7. Far away from the sensor, the electric field fades to 0, so at the external boundary I specify 0 electric potential. Okay. Stylus is a conducting body with unknown potential, so for the stylus boundary I specify floating conductor boundary condition. Transmitting electrode electric potential is plus 1 volt, and receiving electrode electric potential is 0. Before I could start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. Here you can see the equipotential lines. Let's zoom in. You can adjust the field picture and switch on the color map of electric potential. Blue color corresponds to the 0 electric potential and the red color corresponds to the electric potential of plus 1 volt. Okay, my task is to find the capacitance. The capacitance is the ratio of the stored electric charge to the potential difference, or you can calculate the capacitance as a double value of the stored energy divided by the potential difference squared. To calculate charge and to calculate the energy, I should build the integration contour. So I will use the contour tool, click to select the air, click to select the dielectric board, follow to the integrals, and here is the stored energy. And the capacitance is this value doubled divided by the potential difference squared. So it's simply 2 multiplied by 0.8 picofards. In fact, there is no need to calculate it manually. In QuickField you can use the capacitance wizard, specify the electrode, calculate the energy here, and this is the capacitance value. (0.817 picofards). I have calculated the capacitance for this specific stylus position. What will be capacitance for another position of the stylus? That I can do easily. Open the geometry model, zoom in, right click, move selection, displacement to the left by 0.2 millimeters. Okay. Again, build the finite element mesh, save all problem files, solve the problem, open the results, follow to the integrals, capacitance wizard, next, and this is the new value of the capacitance. It was 0.816 picofards, now it is 0.839 picofards. To measure the distance between the sensor and the stylus, again you can use the contour tool. Let's zoom in, contour, click here to select the edge, contour length. That's the capacitance value calculated for the base position of finger. I can copy these values to the table. And repeat the calculations for other positions of the finger. But there is a way to automate repetitive tasks. I'm going to use the label mirror tool. Label mover tool is used to move labeled objects and calculate integrals for labeled objects. To be able to calculate the distance between the stylus and the sensor, I need to assign a label to this edge. Click here, distance. There is no physical meaning in this edge, it's just a text label. So I do not specify any physical properties here, just click OK, and you see the 0 mark next to the label name. That means that this label doesn't affect the field distribution, doesn't affect the results. OK. Save all files. In label mover, I should specify the base problem, which is sensor PBM. Then I should specify the values to measure. I would like to measure the length of the distance and the stored electric field energy. I need to use a compound counter. Add dielectric block. This would be the compound counter. And for this counter, I will use the stored energy. Okay. Next, I should specify what I'm going to change in the geometry model. I'm going to move the stylus. Stylus move to the left by 0.1 millimeter. Add step. A new problem was created and a new geometry model. And in this geometry model, indeed, the stylus was moved to the left by 0.1 millimeter. Next, I'm going to repeat this step. Repeat while possible, till the stylus hits the sensor surface. Okay. Now that's all. I have the base problem, I have values to measure, and I have steps to perform. So let's calculate the results, get results. In the background you can see QuickField and a series of problems is generated. In each problem the stylus is placed in new position. Then the problems will be simulated and the distance between the stylus and the sensor and the stored electric field energy will be calculated and placed here in the results table. 7 problems were simulated and the results you can see in the table. I can take a look at the plot, distance, energy. The closer the stylus is moved to the sensor, the higher the energy. And capacitance. I can copy all the results to the table to make some post-processing here. Distance, energy, capacitance. Energy value doubled, divided by the potential difference squared. Potential difference is 1 volt. And here you are. If you search for the touch sensor capacitance on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and you can download the simulation files here. Simulation files may be opened and the results can be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.